Well, thank you very much. Buongiorno, everybody. Welcome to this talk, which is not about migrations, which is unusual for me, and is only a little bit about channels, so we're almost on a new topic. But first of all, who am I? I'm the person whose remote isn't working. There we go. So I am Andrew Godwin. As you sort of heard there, I'm a Django core developer. I was the primary author of South, the migrations framework, for many years. I believe it's been about a decade since I started that, which is a scary prospect, to say the least. I'm also, on my day job, a senior engineer at Eventbrite, which is a sort of big online ticketing platform, for those who don't know it. And a lot of my job there, as the sort of years have gone on, has become more and more about software architecture. And one of the things I want to talk to you about is one of the things we're doing there, and one of the things that many companies are doing in general is services and sort of architecture around services. So I'm sure many of you are familiar with the monolith, a single application where everything is bundled in. This is how Django comes by default. You have a Django application, all of your apps and stuff are installed inside the one big sort of Python project. You run it under one WSGI server. It sort of just sits there and does all the right thing. And it's quite good, it's quite easy. You can sort of easily call code from other places. If you've got a handy function somewhere that you want to reuse, you can just import it and use it directly. But there is a few downsides. There's no separation. It's very easy to get spaghetti code where suddenly the nice clean application you had is strewn across 4 or 5 different files. And also you can get nasty side effects from other code. It might be that one of your great new performance optimizations that you did over in part A actually happens to cause real big issues over in part B. And so the proposed answer to this, at least in theory, is services, or as some people call them, microservices. Now, the main difference between the two terms is one is very small services, hence the micro, but the principles are very similar. The idea is you take this code, your big monolith, and you divide it up into separate code bases that run entirely separately. So, for example, you might have, well, here is our user registration service, which is a different code base, a different set of servers, a different database to, say, our order placement service. And that's sort of the basics of how you do it. And one of the ways you do this is you sort of take all that code you have in Django apps, and Django apps are a really good stepping stone for this. And you take them and you start deploying them separately. This means, as one of the good side effects, you can have different dependencies. Say one of your apps depends on an older version of Django, you could run 2 different versions of the Django ORM in production. Not that anyone would do that, of course. It also means they're much more isolated. And this can be both good and bad. So let's look at some of the reasons why you would choose services and some of the reasons you wouldn't choose them. So first of all, and this is, I think, the primary reason most companies go for them, is they're easier to manage, not just in code, but also in terms of managing engineers and staff. A smaller self-contained problem is always easier than a whole giant big problem. And having 4 or 5 small problems is a much easier concept. Small companies, especially startups, are very built around doing small, self-contained things, working fast as a team. And so when you get to the point where you have a big, unwieldy code base, it's a very natural reaction to go, we'll just make this big one into 4 smaller ones, and we know how to solve that problem. And so this is one of the easier things to do. And it definitely does help. Like having a team able to focus just on their area and not worry about other parts of the code they might be breaking can be really beneficial. Independent scaling is another big thing as well. When you have this code running on different servers, you can easily look and say, well, clearly, our user registration flow, it's using half of this one server, it's fine. But over here, our thumbnailing service is like maxing out these 5 different servers. And so you can easily say, well, we'll increase that amount of capacity and not the other one, and not just waste money on, well, we need to run more of the big monolith app and have 700 megabytes of RAM used by each single WSGI worker. So that's a sort of big improvement that a lot of operations people like to use. You also have faster deployment. As your application gets bigger and bigger, it gets harder to deploy. You've got to build a new virtual VM, you've got to check the code, run the tests. All of these things are faster with a smaller service. And so you can take what might be a 10, 15-minute deploy for your big monolith app and turn it into a couple of minutes and get back to that nice, fresh, quick feeling. But there are problems as well. And the number one problem is very complex interdependencies. You remember I said that you can take those nice Django apps and make them separate? Well, that's true. And all the work that you might have had to do with fixing things calling across processes or interactions. It hasn't gone away. It's just gone from being in your code to being in your deployment process. If I have 4 or 5 services and they've all got a new release, what order do I release them in? Does this new ordering service depend on this new user service? What about this other one? You can get into a case where you actually have something that's impossible to deploy because there's a circular dependency of new versions. And in development, it's not a problem, but when it comes time to push the button in production, you quickly find that you just can't push through it without doing them all at once and sort of crossing your fingers. It also requires a lot of communication. And this is often where the management part falls down from that first point I mentioned. Having services implies that you have an excellent boundary, that the place where the services talk to each other is well defined, which means that teams have to A, write documentation, which I bet most of you don't do because it's hard, right? And B, they need to talk to each other, which engineers generally not so great at in general. And so you end up with a situation where code that previously existed that was sort of loosely defined, and we're like, okay, well, we have a bit of a contract here, suddenly needs to be made very rigid. And you start needing to define those boundaries in written terms, or at least in very firm terms. You need to communicate changes almost like you're doing third-party APIs to people who don't even work in your city. There's also way more points of failure. Some people seem to think that services makes things better for failure modes. That's not really true, because generally you're not designing services so that if any of them fails, you can keep going. I mean, that's the ideal, but most services, if one of them fails, the whole site is down. And so now, rather than just having a whole load of homogeneous servers that you can reuse, and if one goes down, it's fine, you have these 7 or 8 different points of failure where, oh, well, this service is down, everything's broken. And it just leads to more and more complexity. And then there's one that's either a positive or a negative, depending how you see it. You can't hack things in quickly. I, in my sort of grumpy old man phase of, I'm not old enough yet, but I kind of am, see this as a positive. You can't quickly hack in changes. Because of the way services work, the separation they enforce, the way that stuff happens, you just can't go in there and quickly fix a bug because it might need different services. You need to fix the contract, you need to fix the API, and that's not really easy anymore. So let's go through what that process looks like. How do you take a Django project that's grown up, that's started as a small single project, and then it's now got to a sort of an unwieldy size? The first thing to do, and the most important thing to do, is work out where you're going to slice it up. What are you going to turn into services? As I said, in Django projects, the apps are generally a good idea if you've kept a sort of clean app schema, but it might be something a little bit harder. Here's a sort of very vague example from Eventbrite's history. So Eventbrite, of course, is a ticketing platform. This means that you purchase tickets, we charge your credit card or other payment type, and then we sort of send you ticket barcodes in your email. And so the old site looked sort of like this. There was one function that made a new order row when you click the start button, sort of wrote some tickets to sort of a preliminary state. Another function then took those rows, worked out how much they cost and charged your card for them. And then a third function, when that had finished, went, okay, the payment's gone through, we can mark the order as final and send the barcodes. Unfortunately, this is not quite the split we wanted for our service design. And so you had to take these things and first of all, ply them apart into slightly more granular items. So here you can see we've taken up things like making the order row and allocating inventory and made them separate. And this means we can then take these separate items and turn them into 5 different services. So in order here, we have an order service, which is how we sort of manage that flow of, I want to start a thing, I want to stop a thing, I have an ID. You have an inventory service because the challenge is you have to sell exactly the right number of tickets, and the challenge of selling the right number, having transactions, is in itself enough of a challenge to warrant its own service. You have a pricing service because, let me tell you, pricing tickets is very difficult. I think airlines might be harder, but only just. Sometime come and ask me about all horrible fees people want to add on. It's not our fault, trust me. And then finally, you have a payment service because, again, trying to charge payment instruments is really difficult. So credit cards might seem simple, but what about things like, oh, in South America, you pay and then you get a barcode and you go to the post office and give them roughly the right amount of money and it's considered settled at that point. Like, there's a lot of different variations on payment that have to be supported. And all of these have separate teams on them now. And so by taking those initial bigger blocks and splitting them out, we now have this separate flow. And a big part of this, as I said before, was defining those APIs between services. How does the inventory service understand how to lock and unlock seats? Like when an order is placed, how do you call it to say this? How do we change that? How do we tell the other teams how to change that or when to change that? Do we have compatibility periods? Like, we have over 100 engineers all working in 4 different locations around the world. It's hard to communicate. We were in 4 different time zones. It can be difficult. The other big thing is to separate your data stores. Going to services is great. It helps make the code and sort of the CPU usage a lot separate, but it also means that at some point you need to move your database and other data stores to be separate as well. We still aren't at that point yet, but the idea is that you would separate, say, oh, this is the place where tickets are stored from this is the place where user passwords are stored. And then you have different security levels and different levels of uptime or looking at for each of those kind of stores. So that's the basic idea about services. But the crucial thing is, how do you talk between them? Say we have 3 services, and this is very optimistic. We have like over 30, I think. I heard at one point Uber has 2,500 services for reference. So you have 3 services. You need to talk between them. Well, how do you do that? There's no sort of defined standard for this in the world generally. The first sort of naive option is direct communication. Often this is done using HTTP because that's easy. We have WSGI servers that understand that stuff. And it's pretty simple to set up. There's a little bit of difficulty with working out the addresses, but it works out all right until you get to a large number of servers. Now, I'm not sure quite how to describe the function mathematically that this goes up by, but it is, in Python, the sum of the range of the number of services. And so with 3, you have 3 connections. With 20, you have 190 connections. And bear in mind, every one of those connections is a possible failure path. So you can see, like, as you increase the number of services, it goes up, and I'll say exponentially. I don't think it's actually exponentially, but it goes up incredibly fast. If you had over 1,000, I dare to think what would happen. And so the first step with this is you go, okay, we don't want to hard code IP addresses or DNS names of those services in. We'll have a discovery system. And so you go, hey, I want to talk to the user service. You go to the discovery system, say, hey, where is the user service? It gives you an IP address. This is where you can do load balancing as well by giving a range of IP addresses. And then you still connect directly to the service. It's an improvement. It's more flexible. It means you can launch 4 or 5 boxes with the same service on and sort of bring them in and out again easily, but it's still not particularly great. The next step you can do is centralized routing, where all the services talk to a central routing server, a process, or even a router, but don't know about each other. And this could just be using DNS properly in some cases. But here you have a lot less configuration and a lot less state, which is very useful. But this is really the sort of, along the road to the final one, which is the message bus. And this is what I'm sort of going to talk more about today. A message bus is an application or a cluster, but basically it's a thing. Your service and your website, everything else talks to the thing. You send a message onto the thing with a destination, and then the receiver gets them back with the right name. TCP and UDP are kind of like this, but a message bus is a bit different. It has storage, so generally you can store minutes to sometimes even hours worth of data, which means you can do things like take down all of the servers on a service and bring up new versions, and those messages will wait on the bus for the new things to come up. So it gives you sort of graceful restarts. It also gives you better control over sort of flow and capacity, as we'll see later. But essentially, it's taking what networking is and making it very specific to the application that we're doing here. And there are always trade-offs. So what I just showed you was a trade-off. And in distributed systems, which is what this is, by the way, there's always trade-offs. There's never a good solution. So here you've seen centralized communications versus distributed communications. Centralized being message bus, distributed being direct connections. Centralized is great for ease of use and configuration, but it's a single point of failure. You have that centralized routing thing that if it goes down, you're basically screwed. In the obverse, you have distributed stuff where you have all this sort of apparently redundant communications, but now you have 190 different connections to debug. If one of them disconnects or slows down, finding it's much harder than working out your single central thing has gone down. So that's just one example of a trade-off. Another example is one I push a lot, is what kind of delivery do you want? You cannot, and trust me, if someone claims this, they're lying, you cannot send a message exactly once. You can either send it at most once, where if you fail, it just doesn't get delivered, or at least once, where if you fail, it gets delivered more than once. So for example, imagine a system like UDP, where you send it and hope for the best, that's at most once. Something like, say, Kafka, which has an ACK, where it's like you send the message to the thing, it has to acknowledge it's got it back again. That is at least once, because sure, you can send it, but if the acknowledgement fails, you're going to resend it to the next client again, so you've delivered it twice. So this is a big trade-off. This is probably the most fundamental one because it's how you write your application code. It affects your design of your system fundamentally. How do you deal with failure? Like, for example, if you're placing orders, do we want orders to try twice? Do you want cards to be tried twice to be charged? Or do you want to try them nothing? Just leave them and not charge it and deal with it later. So that's really a call based on the situation. Channels in this case goes for at most once, and I'll describe more of why that is later. Another interesting trade-off, and this isn't necessarily obvious to some people, is the kind of message queue you have. Most people think of a queue as first in, first out. That is, the first message into the queue is the first one that gets received by a client. They're in order. It makes a lot of sense. However, this does have an interesting side effect that when you have a huge rush of traffic, everything is backlogged equally. All the traffic that's piling on behind your first one is delayed by all the traffic in front of it. You can instead go for a first in, last out system, which is usually, it's more of a stack than it is a queue. But what this means is if you're backlogged, new requests still get served very quickly because they're on top of that heap, that stack. But it also means that the things at the bottom of the stack get really, really latent. And so it really depends, like, do you want to always have a good experience and then let the few people who drop out have a really bad time, or have more of an equal experience for everyone when things are going bad? So another case of the trade-offs. And how does it relate to channels, and in particular ASGI? So for those who aren't familiar, channels is the name for a whole group of projects inside Django. Oh, the slide's gone away. Okay, I can try and describe them, it's not going to help. Let me try and replugging in here again. So the monitor here is showing it still, that's why I'm confused. There we go. Okay, we're back. Lovely, what a lovely picture that is. You've missed the picture. Okay, back with where we were. So, as I was saying, channels is part of a bigger set of projects. Channels is the name of a big set of projects inside Django. So the thing that you think of a channel is actually 4 or 5 different things. And this is a slide from an earlier talk I gave last year. But basically, channels is the combination of a protocol server, which is a server written in Twisted or Async.io. It's fully asynchronous. It handles terminating HTTP or WebSockets for you. It's the combination of that, a middle channel layer, which is the message bus in this situation, and then Django workers. And channels is the name of all 3 of these, but the protocol by which they talk to each other, the thing the channel layer in the middle is built on, is called ASGI, which is a backronym for Asynchronous Server Gateway Interface. Don't blame me, actually do blame me for that one. So the idea is that, sure, in the normal channels world, in what you probably think of as a WebSocket world, we use that underlying message bus to do WebSockets. We turn WebSockets into a series of messages on the bus, we pass them to and from Django, and then code either end makes it look to you more like HTTP. Inside Django, we have code that takes the messages, decodes them into a request, and re-encodes them from a response. And in Daphne, the server, we have code that takes these on-the-wire HTTP requests and turns them into messages. But what you can do is you can throw away all of that, no one wants that stuff, and just use the channel layer. Because the channel layer itself, the ASGI specification, is defined. It's a very simple spec. It has a send, it has a receive, and it has a couple of other things to do with groups. And so if you want, you can just reuse all this work we've put into making all this code. Like we have a Redis backend, it scales, it shards. There's a RabbitMQ backend being worked on as well. There is in-memory testing backends. All of this work you can reuse and use yourself and do it with service communication. And this is what we're doing inside Eventbrite. What you can do is take the channels that you may be familiar with WebSockets and use them in a very similar way for doing service requests, where you send a request on a single name channel, then a whole series of servers listen on that channel, one of them picks up the request, and then writes a response back to a client-specific channel. It's pretty easy to do. There are some trade-offs, obviously, as I explained before. ASGI has built into the specification at most once delivery. It says, if you do not deliver the message, you must fail rather than try twice. This is because, in my experience, it's a lot easier to write for missing than duplication, but you may disagree. It is also very low latency. Generally, the end-to-end latency of channels is around 1 or 2 milliseconds. This is great for real-time stuff and protocols like WebSockets and services. It's quite bad for things like task queues. If you have a queue of things that must get done but quite slowly, you want Celery. You do not want channels or ASGI. And finally, it has things built in for capacity and back pressure. So a channel has a certain size, about 100 by default. And if you try and push more things into a channel that's full up, it gives you an error. It says, no, I can't do that. The trade-off here is that it means your apps have to deal with failure to send. We raise an exception you deal with, but it means that you get to know what's happening. So for example, if Daphne sees back pressure, it sees the channel is full, it says, oh, well, the servers are busy, and gives you a 503 error back to the client. So you know, okay, there's server problems, and we've got rid of that connection. We're trying to get rid of the backlog. And so feeding into this, I want to give you a few tips for both using channels and just in general doing service-oriented architecture if you're interested or starting out with it. So the first thing that I found very useful that was done before I joined Eventbrite was a thing called correlation IDs. Now what this is a random UUID or other random string that's passed through an entire string of service calls. So say you make a web request. Your web request goes, okay, I need to render a nav bar, so I'll call the user service. I need to render this event page, I'll call it an event service, and all that sort of stuff. But the request has an ID, and that ID is given to those services, and if services call other services, they pass the ID along. And so you end up saying, okay, what things did this page request call? I can just look up all my logs with the correlation ID and see every single request call that routes back and starts at that page request. The same thing for API requests as well, or mobile app requests. And so if you're trying to debug, because debugging is very hard when you've got 30 repositories, let me tell you, this helps you a lot work out what was called and when it was called, so you can try and trace down the error a little bit better. Another thing is feature flags. Quick show of hands, who here uses feature flags? Hands up. Oh, it's about a third of the audience, I'd say there. So first of all, you should all use feature flags, they're great. There's many other talks about that stuff. But if you are going to use them, an important tip for services is don't have a database that every service queries. Because you've now made another single point of failure, and moreover, every single service, every single machine in your company is going to call that server. The trick instead is to bundle all the feature flags in with a service call. So like that ID I said, we have a sort of a header of message information. So when you hit the website or an API, we then at the boundary work out, okay, these are the flags you have set, and then pass them on, and they're sort of transitively given to every service in that call stack. So there's one call to the database, not hundreds. Another key thing is source of truth. It's very easy to wander into breaking up a monolith and just making services that all still call the same database. The worst thing is when you have two different services that both write to the same table. You still then have two different code paths that you can't share code between that write to the same store, and it gets horrible quickly. So one of the key things to look at is make sure that at worst, only one thing writes to each table, and preferably only one thing reads from each table as well. If you have caching or other logic, make sure it's all encapsulated into one service so that you can treat it almost as a black box. Like, well, I want to get event data, I just call this thing. All the caching and invalidation is done for me. Metrics are very important. As I said, debugging is very difficult when you have all these scattered repositories, and also performance is critical because you can't scale one thing anymore. So you need to make sure you put metrics at minimum sort of request times and how many requests are happening. You can dump those into Graphite, for example. But just have some idea of like how each individual component's performing so you can tune them or tweak them as well. It also helps to capture things like every developer's nemesis, slow networks. It's not disconnected, it's just very slow, and so your code won't catch it. Another very important thing that I encourage everywhere is design for failure. If you design for failure from the get-go, then when it happens, you'll be prepared. You'll be good. Like, expect that anyone could come in and turn off all your machines at any random time. The Netflix Chaos Monkey is the pinnacle example of this. So if you design for things to go down randomly or things to vanish, when it does happen, you'll be ready for it. Whereas if you say, oh, well, we'll assume this always works and fix it later, you'll get caught by surprise. And finally, and most importantly, do not start off writing services. I say this as somebody who has now worked on a few projects that use them. It is a fool's errand to try and start off with lots of microservices, at least in my opinion. The operational overhead of running all those individual machines is really quite large. The best thing to do is to write as if they were services, that is to write separate code in separate Python packages, preferably with their own setup.py modules, install them in their own requirement stuff, and don't share code, but run them on one machine. And then as the time comes to scale up, to increase your operational complexity, then you can start looking at how to transport stuff. Otherwise, you're just introducing points of failure into a system that, to be honest, doesn't need any more of them. And with that, thank you very much. So I believe there is a short time for questions. Okay. Okay, go ahead. Oh, right. There we go.
Thank you. Awesome. Can I just ask you to talk for a few moments on an outline of how you handle retrying in application code, because you're not asking the channel layer to do it.
Right, exactly. So that's the trade-off, right? So there's no retries in the channel layer because it's at most once. And so it depends on the application. So if it's critical, for example, it's payment related, you build application logic for retries where you have that acknowledgement process built in. I can't speak to specifics, unfortunately, because I'm limited to what I can talk about internally, but we have extra application layer logic around stuff that is critical to be retried, and other stuff that, like, say, if we're trying to show you just to show you a page of information, we'll just drop the page and say that's an error, because we'd much rather not backlog and get out of a hole if there is one. No problem.
Hello. Hello.
Hello.
Thank you for your speech. And what tools do you use to describe all your services, to describe all your APIs, contracts, and so on?
Yeah, so that is an excellent question. Right now, the answer is not enough, or rather none. Generally, description is done on an ad hoc basis in documentation and Google Docs and things like that. I would love to have a formal way of describing that stuff, and there are many examples of this, like JSON schema and things as well. We have an internal solution we are looking to release open source that defines proper schemas for all this stuff that is advertisable. It's like, oh, hey, here, this is a service call, here is the schema in sort of a Pythonish language, here's how you can introspect it, but we haven't, that's the plan. Currently, it's a little bit more loose than that, I would say. Cool. Any more? Oh, one more.
Hi. So will Django channels be included to the core of the Django? that question was raised before it was released like stable version, and you answered that no, it's not ready yet. And what's the future? Would it be like in the contrib or somewhere else? Thank you.
That's a very difficult question for me to answer. The answer is I don't know. Part of me is like, at some point we can move it into core. Part of me is like, it's perfectly fine as a third-party package. Like, it's still an official Django project right now. That's the difference. So I'm very split into, we couldn't. It's really a question for the other core developers. I'm too close to it in many ways as well. I think the middle answer is there are some parts of it I'd like to include, but probably not the whole thing. Is probably where I'd fall on that.
So it's likely to be like a contrib.
I couldn't say. Like, I'm not a fan of contrib in general. So like, I'd like Django core to be smaller, is my personal experience, and to be the person who doesn't do that is kind of self-conflicting in a way. So it's a very difficult question, and I haven't really decided.
And currently, Django channels, like, you think it's stable? I mean,
yes, it's stable. It's at 1.0. It's at 1.1 or 1.2 now. Yeah, it's stable. It's production ready. People use it in production. It's got a Django capacity. Like, we have a backwards compatibility policy as well. We have security policies. It's all there. It's just not in Django core. That's the difference.
I'm using it in production too.
Yeah. Okay.
Thank you.
Thank you.
Hello.
Hello.
I just wanted to pick up on a thing you're saying about writing multiple Python libraries and running them on the same server. Will you still be using a message bus at that point, or would you be just like importing them and calling them, or are you still running separate processes on the same server?
So those are sort of different levels. Like the first thing I do is just call them directly in Python without a message bus. Right. The second step, which I advise, is to run them through a serializer, like JSON or message pack, but don't actually send them, to make sure that what you're sending is actually serializable. So we did this for a while at Remember. It's like, oh, well, we're not sending them anywhere. They're still in memory, but they're being serialized and deserialized along the way to test that works. And then you can move to the local machine, and then you can move to a cluster. Sort of just take it in stages, and you get used to each section is what I advise with that stuff.
Last question. To pile up on the libraries, how well does it work out for you, given the fact that you usually have like fine-grained interfaces on a monolith and then go to coarse-grained when you go to remote to reduce latency and everything? How do you encapsulate that in the library in the intermediate step before you go fully remote?
Right. So what we've done there, and my advice is to make the libraries more coarse-grained as you go along. So in particular, the validation library we have for services also works on Python functions natively. So what we can do is actually start wrapping those around the functions in libraries first to enforce that sort of strict, big, coarse-grained separation, and then start taking those big chunks of code and move them into a separate service as it goes along. But yeah, like it's a process. If you have fine-grained code, you have to change it first and split it up as I showed before you can go anywhere else. All right. Thank you, everyone.